Okay, so for every single question in chapter 6/7, you want to ask yourself just a couple of questions. The first thing you want to ask yourself is, am I looking for a percent or probability? If I am, I'm going to use the normal CDF command. Okay. Or do I have the probability and I'm looking for a value? Do I have the percent or probability? In which case I'm looking for a value, then we're going to use the inverse normal. Okay. If you are using normal CDF, the next thing you want to figure out is it a sample? Am I talking about a sample? The probability regarding a sample. If I am, I have to make sure I change my sigma to the sigma over the square root of n. That's if I'm talking about a sample. Otherwise, my sigma is just going to be the sigma given in the problem. Okay, so this is the I guess the three questions we have to ask ourselves every time we do a question in this chapter. All right, so I just compiled a bunch of different examples, and you'll see that those questions apply to each of them pretty easily. So this says a company XYZ knows that the replacement times for the DVD players it produces are normally distributed with a mean of 9.4 and a standard deviation of 0.9. Find the probability, so we are using normal CDF, that a randomly selected DVD player will have a replacement time less than 7.1. So we're finding the probability, so we're going to use normal second distribution normal CDF. So we're looking for the probability that X is less than 7.1. Not a sample, just one individual DVD player. So if we're looking for a probability less than something, there's no lower bound. So the lower bound is just going to be some large negative number. Basically, you're plugging in quote unquote negative infinity. So we usually do like negative a million, negative 100,000, whatever, it doesn't matter. Just some large negative number. The upper bound is going to be 7.1 because we're looking for everything 7.1 and below. So from 7.1 to negative infinity, basically. Our mean is the mean given in the problem, 9.4, and our standard deviation is 0.9. Since we're not talking about a sample, it's just the standard deviation given. So we get a probability of 0.0053. Don't worry about z-scores. We're not using z-scores. We're using the calculator. So then this says, if the company wants to provide a warranty so that only 0.7% of the DVD players will be replaced before the warranty expires, what is the length of the warranty? So we're looking for the X value that cuts off the shortest 0.7%. So here we have the percent, and we're looking for the X value. So we're looking for the X value that cuts off the bottom 0.7%, which is 0.007. So we have the percentage. We're looking for the value. That's going to be inverse normal. Second distribution, inverse normal. First thing it asks is area. No matter what we're talking about, it always wants the area to the left of the value we're looking for. So since we're looking for this X, the area to the left of it is 0.007. The mean is still 9.4 and sigma is still 0.9. We get 7.1885. One decimal place, 7.18 or 7.2. Okay, that's like all you're doing every single time. So now this says scores for a common standardized college aptitude test are normally distributed with a mean of 488, standard deviation of 96. Randomly selected people are given a test. Assume for sake of argument that the test has no effect. If one person one of the people is randomly selected. Find the probability that their score is at least 553. We're looking for the probability. We're going to do second distribution, normal CDF, at least 553. So 553 or larger. So our lower bound is 553.3. There is no upper bound, so we just put a large positive number in. Our mean is 488, and our standard deviation is 96. So we get the probability is 0.2482. Now this says the probability that 7 people are randomly selected. We're talking about a sample now. Only thing that changes when we're talking about a sample is our sigma becomes the sigma of the population divided by the square root of the sample size, divided by the square root of 7. That's just from the formula on the first page of these notes. We hit paste. Now we get a probability of 0.0359 or 0.036. Okay, if the random sample of 7 people does result in a mean score of 553.3, is there strong evidence to support the claim that the course is actually effective? So generally speaking, we always compare this percentage to 0.05. So them getting a score above 553 just purely on luck is about a 3.6% chance. So it's pretty unlikely that they would do it purely out of luck. So if it does happen, then we could safely say that it's probably because of the test prep course. So since it's so unlikely, this is about 4% chance of it happening. If it does happen, that means that it must have been by the result of the test prep course, because them just having it by chance is so unlikely. So yes, the probability indicates that it's unlikely by chance. So the randomly selected students should have gotten a higher score based on the test prep. Okay, a company produces steel rods. The length of the steel rods are normally distributed with a mean of 137.8, standard deviation of 0.9. For shipment, 25 steel rods are bundled together. That's a sample. We're looking for the probability that the random sample is greater than 137.9. Normal CDF, greater than 137.9. So 137.9 up to some large value. Our mean is 137.8. Standard deviation is 0.9, but we do 0.9 divided by the square root of the sample size, divided by the square root of 25, or divided by 5. We get 0.2893. Okay. We already did one similar to that. Okay, engineers must consider the diameters of heads when designing helmets. The company researchers have determined that the population of potential clientele have head diameters that are normally distributed with a mean of 6.9, standard deviation of 1.1. Due to financial constraints, the helmets will be designed to fit all men except those with head diameters that are in the smallest 3.4% and largest 3.4%. Normally distributed, so they follow the normal curve. So we're looking for, what is the mean here? We put the mean in the middle, 6.9. We're looking for the X value that cuts off the bottom 3.4%, which is 0.034. And we'll call this X2 that cuts off the top 0.034. So we have the percentage. We're looking for the value. Second distribution, inverse normal. Let's do X1 first. The area to the left of X1 is 0.034. The mean is 6.9. Standard deviation is 1.1. So we get a minimum head size of 4.892. One decimal place would be 4.9. So now I'm going to find X2, but remember I told you that when you do this, it asks for the area and it wants the area to the left. So if you put in 0.34 again, you're going to get this value. So instead, we're going to do what is 100 or 1 minus 0.034. We get 96.6. That means if there's 3.4% above this, there's 96.6% below it. So when I do second distribution inverse normal, I'm going to plug in 0.966 and everything will be the same. So my larger head size will be 8.9. Okay, and that should get you started on some of those questions.